Hello and welcome again to my physical science online video lecture supplement series. In today's video, I'm just going to work through a set of examples. So today is one of those worked examples videos. And specifically, we're looking at examples for the electricity and magnetism unit of our course. So let's step to it, shall we? So again, these examples are for electricity and magnetism. That's from chapter 8 of our Shipman, Wilson, Higgins, and Torres physical science textbook. For doing these examples, we might want to review a few of the important equations. So again, these equations are presented just before the exercises section of the text at the end of the chapter. And of course, they are also found within the notes and within the text itself. We have a few sets of important equations because we have also equations that go with resistance in series, resistance in parallel, and transformers. So now that we've had a chance to review all those equations, let's look at the actual examples. Alright, for our first example, we want to know what is the force between two charges of +1 coulomb each, which are separated by a distance of 2 meters. So this right here is actually an image from the MIT Museum of a Van de Graaff generator. Usually you set it up so that you have a positively charged one and a negatively charged one, although in principle you could set it up so they are both positively charged. Obviously this is a distance somewhat greater than a meter, and they're probably going to hold more than 1 coulomb's charge, but just to give you some visual. To answer this question, we should look back at our sets of equations and find that we have one that says that the force between two charges is some constant times the charge 1 times charge 2 divided by the distance between charges. That's this equation right here. And that proportionality constant is called the Coulomb's constant. It's about 9 times 10 to the 9th Newton meters squared per Coulomb squared. You may have noticed that this equation has a very similar form to Newton's law for universal gravitation, albeit with a g here instead of a k and with masses here instead of charge. It's because it has, in fact, the same general form. So let's go ahead and calculate how much force is between these two charges. Alright, so we write that force is going to be equal to k times q1 times q2 divided by this distance between q1 and q2 squared. So if I was going to draw this as a diagram, here's charge q1, here's charge q2. The distance between them would be r, and we were given that q1 and q2 are both 1 coulomb. So that's what's going to go in for Q1 and Q2. K again was approximately 9 times 10 to the 9th Newton times meters squared divided by coulomb squared, where a coulomb is this unit of charge that we're using. So let's go ahead and stick all those numbers in. This force is going to be 9 times 10 to the 9th Newton meters squared per coulomb squared times 1.0 coulombs times 1.0 coulombs divided by the distance, which was given as 1 meter. 2 meters. So that's got to be squared. So out comes the calculator, because in physical science we don't know how to multiply mentally as well. So we need to take 9 and multiply it by 1 and multiply that by 1 and divide that by 2 and divide, excuse me, this should be divided by 2. So now we divide by 2 again. Okay, so that gives us 2.25, and then we don't have any powers of 10 outside of this one, so this looks like we're going to have a force of about 2.3 times 10 to the 9th newtons. And again, I rounded it off because of significant figures. The calculator gave us 2.25, but we only have two significant figures to work with, so that's why it's going to be 2.3 times 10 to the 9th. It might be instructive for some of you to go back and review Newton's law for gravity and rework this problem in terms of what's the gravitational force between two masses of 1 kilogram each if they're separated by 2 meters. But I'll leave that as an exercise to the viewer. So in this case, our electric force is about 2.3 times 10 to the 9 newtons. Okay, next up we have a problem that deals with the Bohr model of hydrogen, basically of a simple atom. We're given the Bohr radius, which is basically the distance between the proton and the electron in a simple Bohr model hydrogen atom. And this turns out to be basically the most probable distance between the electron and the proton when the atom's in its ground state. In any case, what we want to know is what's the electric force between the proton and the electron when they are separated by this distance. To do that, we go back to our Coulomb's law equation. Force equals some constant times charge 1 times charge 2 divided by the distance separating them. And that constant again is the Coulomb's constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared. So what do we need in order to solve this problem? Well, we were given the Bohr radius, so that's what's going to go in for R. We don't have the two charges, but we were told that it's an electron and a proton. So we can, of course, go to table 8.1, which is in your Shipman, Wilson, Higgins, and Torr's physical science textbook. And this table 8.1 gives us the mass and the charge of electron, proton, and neutron. So this is the relevant information for this particular problem because here is the charge. 1.6 times 10 to the minus 19 coulombs for an electron, 1.6 times 10 to the minus 19 coulombs for a proton. Alright, so we can do this calculation now. Okay, so here is in fact the equation that we need, and here's the parameters that we need to put into that equation. So this force is going to look like 9.0 times 10 to the 9th Newton meters squared per Coulomb squared multiplied by minus 1.60 times 10 to the minus 19 coulombs times plus 1.60 times 10 to the minus 19 coulombs divided by 5.29 times 10 to the negative 11 meters squared. Okay, so this means that we're going to have to actually deal with all these powers of 10. So let's go ahead and do that. I'm going to actually do this by taking this 5.29 number and squaring it. So that gives me 27.9841. Reason why I'm doing that is I'm basically just trying to figure out what is this denominator going to be. and I have to square this and I have to square this. So this basically has become 27.9841 times 10 to the minus, since I have a minus 11 and I'm squaring it, I multiply this 2 times this 11, so it's minus 22 meters squared. So now that I've done that, I can go ahead and use my calculator to basically figure out what all the arguments that are being multiplied by powers of 10 give me, and then I can deal with the power of 10. So 9 times 1.6, which was a negative, times 1.6 gives me minus 23.04. Divide that by this 27.9841 number, and so it looks to me like I'm going to get F is equal to negative 0.823324, and I'm going to just go ahead and write that as 8.23324, and then the next digit's actually a 67, so we'll just put a 7 times 10 to the minus 1. Alright, and now let's include all these other factors of 10. So I've got that times 10 to the 9 times 10 to the minus 19 times 10 to the minus 19 again, times 1 over 10 to the negative 22 is the same as having 10 to the positive 22 here. So I need to do some addition with these powers of 10. Basically I have minus 1 plus 9 minus 19 minus 19 plus 22. So let's pull up the calculator again. So let's see here, minus, let's say 1, and that's plus 9, and then minus 19, minus another 19, and then that's plus 22. So the total power of 10 is going to be negative 8. So this basically means that this force is going to be 8.23347 times 10 to the minus 8 newtons. And the fact that it's negative, this minus sign that's in here, just basically means that it's an attractive force. So the two are being pulled towards each other by this force. Before moving on, I wanted to, just for fun, compare what we would get if, instead of looking at the force obtained from this charge, what would happen if we looked at the force of gravity between the two. And to do that, we're going to have to go back to an earlier chapter, specifically chapter 3, which is the force and motion chapter in our Introduction to Physical Science text. In that chapter, we find an equation which describes Newton's law of gravitation. F equals g m1 m2 over r squared. So we need to know the masses, and then g is the universal gravitation constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. So we got to get the masses to put in here. That's the mass of an electron and the mass of the proton. So those masses that we needed were recorded in this nice table 8.1. So the electron has a mass of 9.11 times 10 to the minus 31 kilograms, the proton 1.673 times 10 to the minus 27 kilograms. So we need those two numbers in order to calculate the gravitational attraction between the two of them. Alright, so once again we have a set of numbers that we can plug into our equation. We've got the gravitational constant, so this is basically saying Fg is going to be negative 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And that's going to be multiplied by these two masses. So the mass of the electron is 9.11 times 10 to the minus 31 kilograms. And the mass of the proton is 1.673 times 10 to the minus 27 kilograms. Again, you get those two numbers out of that table 8.1 from your textbook. Then you got to divide that by the distance between them squared, which was the Bohr radius squared. So that's 5.29 times 10 to the minus 11 meters quantity squared. And again, this thing we found in the previous problem, or the previous part to this problem, is actually 2.79841 times 10 to the minus 23 meters squared. So looks like we're ready for that calculator to come out. So pull up our calculator. We have 6.67 times 9.11 times 1.673 divided by 2.79841. So that's 36.32. 693926 blah blah blah. So that means that our force of gravity so far looks like this. Minus, I'm going to convert that 36 into a 3.6, and then might as well get the next couple digits, times 10 to the plus 1, because I went from 36 to this. And now we have all the other powers of 10, so that's times 10 to the minus 11, times 10 to the minus 31, times 10 to the minus 27, times 10 to the minus 23. Whoops, it's actually final unit is in newtons. So now we got to do some simple addition again. So I'll just use the calculator to show you guys how to put those numbers into your calculator for some simple addition, because we're multiplying all these powers of 10. So we have 1 minus 11 minus 31 minus 27, and then this last one is actually a plus 23 because it was in the numerator. It was in the denominator as a minus 23, so in the numerator it's a plus 23. So plus 23. We come out with 3.6 times 10 to the minus 45. So the force of gravity appears to be about minus 3.633 times 10 to the minus 45 newtons. So I did that for the interesting point of contrast. This was the electrical force between the two. Here's the gravitational force between the two. And the thing that's most important here is this power of 10. For electrical force, it was a power of -8. For this one, it was a power of -45. That means that this thing is 45 minus 8, or basically 37 orders of magnitude greater than this one. Means that if you wanted to say how many times greater is this force than this force between that proton and that electron, you need a 1 followed by, according to this, 37 zeros in order to express that number. So it would seem that the electrical force is quite a bit stronger than the gravitational force between our fundamental particles. And it turns out that basically the reason why gravity seems to dominate as the force in the universe on a large scale is because we have about the same number of positive and negatively charged particles, and so they kind of screen each other, whereas mass only seems to be additive. So gravity ends up being stronger in bulk. Okay, so let's look at this next example then. Now we want to know what is the acceleration experienced by an electron which is placed 1 times 10 to the minus 10 meters from a stationary proton. Okay, so this is a pretty tough example for physical science because we have to calculate the acceleration from the force, and we have to calculate the force before we can use that force to get the acceleration. So we're going to need to go back and look at a certain table in order to get all the information for this, but let me set up the problem first. We have two principles that we're using here. The first one is that we're using Newton's second law, which says that force should be mass times acceleration. The second one that we're using is Coulomb's law, which says that the force should be the Coulomb constant times the two charges divided by the distance between the two charges. So we're going to solve for this force using this equation. We'll plug that number in here to get the acceleration, because this one is saying that the acceleration is equal to the force divided by the mass. So if we wanted to, I guess we could just do a further substitution. Since this is F and this is F, the acceleration must be K Q1 Q2 over R squared M. And the thing that's specifically accelerating in this case was the electron. So I'll go ahead and put a little E down here to remind us that it's the electron that's accelerating. So let's go ahead and pull up that table 2.1 so that we can get the values of Q, Q, and M. Alright, here's table 8.1 from your text. It gives us the mass of the electron, it gives us the charge of the proton, and the charge of the proton and the charge of the electron. So those are the three numbers that we needed off of that table. We also need the Coulomb constant. So the Coulomb constant is this constant of proportionality in this equation, K Q1 Q2 over R squared, and it is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so if we plug all those guys in, we end up getting that the acceleration is equal to 9.0 times 10 to the 9 Newton meters squared per Coulomb squared, that's the Coulomb's constant, times minus 1.60 by 10 to the minus 19 coulombs, that's for the electron charge, and then another plus 1.60 times 10 to the minus 19 coulombs, and that's the proton's charge, and then that's got to be divided by 1.00 times 10 to the minus 10 meters, and that is the separation distance, so that's got to be squared. And then we also have to factor in the mass of that electron, so 9.11 times 10 to the minus 31 kilograms. So that's plugging all of our information in. Let's go ahead and calculate what these numbers will be. So pull open our calculator. We have 9 times 1.6, that was negative, and that's times another 1.6, and that is going to be divided by, and I guess I'll multiply all the numbers down here for you as well, 1 times 1 times 9.11, and so you're going to have, this is minus 2.5291, we'll say. So the acceleration is minus 2.5291 times, we have a 10 to the 9th up top, we have a 10 to the minus 19th up top, we have another 10 to the minus 19 up top. We have down below a 10 to the minus 10, which got squared. So this is 10 to the plus 10 times another 10 to the plus 10 times 10. This is the minus 31, so since it's in the denominator, it's a plus 31, and the units should end up being meters per second squared. So where does that leave us? That gives us minus 2.5291 times 10 to what power? All right, time for this. Plus 9 minus 19 minus another 19 plus 10 plus another 10 plus 31. Ooh, it's a positive 22. So big acceleration, meters per second squared. That is the acceleration of an electron, which is initially stationary, towards a proton which is placed 1 times 10 to the minus 10 meters away. So yeah, pretty big acceleration. If you just wanted the magnitude, you can drop that minus sign. Again, the minus sign just tells you that the electron accelerates towards the proton. All right. Question: how many electrons must pass through a wire per second for there to be a current of 1 amp? All right. Well, the current is we usually use an I to represent current, and the current is usually the amount of charge that passes through a given basically cross-sectional area, in this case the wire, per unit time. And so we're basically looking for that. We want to know how many charges are going to pass through the wire per unit time. So therefore we can take basically the current and multiply it by delta T. And so what we have here is 1.00 amp times our 1 second. And an amp second has units of coulombs. So this means that we have to have a charge of 1.00 coulombs. All right. And the sign doesn't really matter here, because if this current is going through the wire, you basically have electrons going in one direction and electron holes, which are a sort of a positive charge of a sort, going in the other direction. So the question is, how many electrons does it take to make up 1 coulomb? Well, the total charge can be given by the number of electrons times the charge of an electron. So this delta Q is given by this. That means that the number of electrons must be the total charge divided by the charge of a single electron. So what we need here is the charge of a single electron. Where do we get the charge of an electron? Well, we look it up in table 8.1. So an electron has a charge of 1.6 times 10 to the minus 19, and of course that's a negative charge. So this right here becomes 1.00 coulombs divided by basically 1.60 times 10 to the minus 19 coulombs per electron. And the signs don't really matter here, as I said before. So what we do is we take our calculator out and we take this number, this 1.60, and we basically divide 1 by it. So 1 over x does that for us. So that's minus 0.625. And this 10 to the minus 19 just becomes a 10 to the plus 19. So this tells us that the number of electrons should be basically 6.25 times 10 to the 18. So that's how many electrons we need in order to make 1 coulomb, and that's also therefore how many electrons we need to pass through the wire per second if we want to have a current of 1 amp. So you need quite a few electrons to pass through a wire to get 1 amp. By the way, you should also note, or it should be noted here, that if the electrons are all passing from right to left in this, then there are electron holes, basically an atom that is missing 1 electron, that are basically the missing electron, the hole, moves from left to right, and that's the direction of the actual current in this wire. Next question, how much work is done to an electron as it passes across a potential difference, sometimes a voltage or voltage drop is what this thing is called. How much work is done to an electron when it goes through a voltage of 1.00 volts? And also, what will the electron's final speed be if it was initially at rest? Well, one way that we could go about solving it is to notice that the unit 1 volt is equivalent to 1 joule per coulomb. So what that means is that the potential difference, delta V, is also going to be equal to the work done divided by the total charge. So what this means is that the work done to the electron should be this voltage times the charge of the electron. So that's going to equal, well, we need to go get the charge of the electron. The charge of an electron is minus 1.60 times 10 to the minus 19 coulombs. So we can actually just drop the sign for this because it's a scalar in this case. So we basically have 1.00 volts times 1.60 by 10 to the minus 19 coulombs. So the amount of work done to this electron is 1.60 times 10 to the minus 19 joules. Wow. The other part of the question was that we wanted to know how fast the electron would be moving in. So remember that the work done is going to be equal to the change in kinetic energy. That's the work energy theorem that was sort of mentioned in chapter 4, the chapter on energy and work. This is also therefore going to be equal to 1/2 m times v final squared minus v initial squared. And the electron was initially at rest, so that means that the initial speed was in fact 0. So what we have here is that the work is equal to 1/2 the mass times the final speed squared. So that means that we can try to solve for the final speed. So we're going to have 0 is equal to 1/2 m v final squared minus work. So now we need to subtract the 1/2 mv squared from both sides. So that means minus 1/2 mv final squared is equal to negative work. And now we divide both sides by -1/2, and we divide both sides by m. So v final is equal to, when you divide by 1/2, it's the same as multiplying by 2. So we have 2 times the work divided by the mass, and we need to take a square root to get rid of the squared on that final speed. So this means that we have square root of 2 times 1.60 times 10 to the minus 19 joules divided by Oh, we need the mass of the electron. So the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So let's go put all that into the calculator. We have 2 times 1.6 times, to enter this power of 10 to the minus 19, we basically go 19, it's minus, and it's 10 to the x. Okay, and then that is going to be divided by 9.11 times 10 to the minus 31. And so we end up with this wonderful number. So that is, I'll just write down all the digits because we're going to have to take a square root of that in order to get our actual final answer. But 3512623490066, and if you do some unit analysis, you get meters squared per second squared. Okay, so now we take that number and we take the square root of it, and we end up with 592,673.9. So V final is 592,674 meters per second, or if you want to put it in scientific notation, 5.92674 times 10 to the fifth meters per second. So that's the total amount of work that's going to be done to an electron, and how fast the electron will be moving after it's moved across a voltage drop of 1 volt. And of course we need to round it off to 3 significant figures, so that becomes 593,000 meters per second. Our next question is, suppose that you have 1 times 10 to the 10th electrons passing through a section of wire per second. So the question is, what's the current that's being carried by this wire under these conditions? So to solve this, we use that the current is the amount of charge per unit time, and the amount of charge is going to be the number of electrons times the charge of an electron per unit time. Alright, so you can go look up the charge in table 8.1 if you don't remember what it is. We were told that there are 10 to the 10 electrons that move per second through this wire. So this is how many electrons there are, and then that's going to be times the charge of an electron. Again, we can drop the sign for this, so 1.60 times 10 to the 19, 10 to the minus 19 coulombs per electron, and then that is happening every second. So the current is going to be 1.60 times, we have 10 to the plus 10, we have 10 to the minus 19, so 10 minus 19 would be negative 9, and then the units are amps. So that is what the current in this wire is going to be. And so of course that is in the correct number of significant figures. You can sometimes, by the way, if you don't like carrying this 10 to the minus 9 here, 1 times 10 to the minus 9 amps is the same thing as 1 nanoamp. So this is 1.60 nanoamps. Alright, so next question. We're told that you need a potential drop of 25 volts to sustain a current of 2 amps in a certain wire. So the question is, what's the resistance of that wire? Alright, so we're into the Ohm's law part of this lecture. Ohm's law states that the voltage drop across a given circuit should be the current times the resistance of the circuit. So we need voltage in volts, current in amps, resistance in ohms. So that means that we can write Ohm's law, V equals IR. We're trying to solve for the resistance because we were given that the voltage is 25.0 volts and that the current is 2.00 amps. So that was what was given in the problem. We're looking for the resistance. So we should subtract the voltage from both sides. So we have IR minus V is 0. We should subtract the resistance, the IR term from both sides. So that's minus IR is equal to minus V. Therefore, the resistance is negative V over negative I, which is the same thing as V over I. So that is going to be 25.0 volts divided by 2.00 amps. So should be 12.5, but so we have a resistance of 12.5 ohms. So we've now got the resistance for the wire and with the correct number of significant figures. Next question, how much voltage is needed to sustain a current of 1.5 amps in a circuit whose total internal resistance is 100 mega ohms? Alright, so we use Ohm's law again, V equals IR, and we've been given that I is equal to 1.50 amps and R is equal to 100 mega ohms, which is the same as 100 million ohms. So this means that our voltage requirement is going to be 1.50 amps times 100 million ohms. So that is going to give us 150 million volts. Or if you'd rather, 1.5 times 10 to the 8 volts. This is the same as saying 150 megavolts is needed to sustain a current of 1.5 amps through a resistance of 100 mega ohms. Alright, so how much power is used by an air conditioner if it runs at 120 volts and draws 14 amps of current? So now we're into the electrical power part of our lecture, and basically there's this nice little explanation for how to figure out electrical power. You have that the power is for an ohmic resistor, P is equal to IV, meaning the power is the current times the voltage. You could also use I squared R or V squared over R. But what we've been given in this problem is that the current is 14 amps and the voltage is 120 volts. So we use that the power is 14 amps times 120 volts. So let's whip out our calculator and figure out that it's 1,680. So 1,680 watts. Now, with that said, we only have two significant figures to work with, so we should round this to 1,700 watts of power. That's how much power is needed by this air conditioner. Alright, how much current is being drawn by a 120 watt light bulb which is operating on 240 volts? To solve this problem, we can use that same P equals IV equation that we just looked at. The power is the current times the voltage. And since we're looking for the current, we need to solve this thing for current. So that means that P minus IV is equal to 0, and that means that minus IV is equal to minus P. So that means that the current should be the power divided by the voltage. The power was given as 120 watts. The voltage was given as 240 volts. So the current needed is 0.5 amps. And again, you need to keep track of significant figures. There's at least 2 in this problem. You could argue that there's a third significant figure, so it should be 0.50 amps, or if all of these if these zeros are significant, then it's 0.500 amps. So the next question, what's the resistance and power of a dishwasher which draws 10 amps from 120 volts? Oh, this one's really hard because we have to use more than one equation. Our first equation is V equals IR. That's Ohm's law. We're solving that for R. I'm just going to solve it for R. I'll leave you to do the extra steps of algebra to get this, but R is equal to the voltage divided by the current. The other equation that we need to use is that power is equal to the current times the voltage. Alright, so we were given that the current is 10 amps, and we're given that the voltage draw was 120 volts. So this means that the power is 10.0 amps times 120 volts. So this is 1200 watts. And then the other one was the resistance, which is the voltage divided by the current. It's 12. So the resistance is 12, probably 12.0 ohms. So this dishwasher has a resistance of 12 ohms and uses a power of 1200 watts. Alright, suppose that you have a light socket which provides a fixed voltage of 120 volts, and we want to know which light bulb will have the greater power usage, one which has a large resistance or one which has a small resistance. So one way of figuring out the answer to this problem, this is almost more of a conceptual quiz than a problem, but you could do it this way, is to figure out how much power is being used by, let's say, a 50 watt bulb or 60 watt bulb, let's say, and figure out what kind of internal resistance that has, and then do the same thing for a 120 watt bulb and figure out how much internal resistance that has. The other way around is to pick 2 internal resistances and figure out how much power draw they would have given a 120 volt voltage supply. So let's do it that second way. So voltage by Ohm's law is resistance times current. Power is current times voltage. So we want to figure out, how does power relate to resistance? So one way of doing that is to solve this for I and then plug in here where there's an I. So this one right here is saying that I times R is equal to V. So that means that I is equal to V over R. So now we can plug it in down here. This is now saying that P is equal to V over R times V. So that's V squared over R. So I think we better calculate it explicitly. So let's use 2 hypotheticals. So the hypotheticals are going to be that R is equal to, maybe we'll make it 100 ohms, and the other hypothetical is that it will be 200 ohms. So let's see which one of those two gives us a bigger number for the power. So let's call this R1 and this one R2. So P1 is going to be V squared over R1, so that is 120 volts squared divided by 100 ohms. So let's plug in those numbers. 120 times 120 divided by 100. Drum roll please, it's 144. So this first one has 144 watts. For the second one, we have P2 is equal to V squared over R2. So that's 120 volts squared divided by 200 ohms. So let's do that. So again, 120 times 120 divided by 200 gives us 72 watts. Question: was this the result that you expected? According to this, the one which has more resistance is drawing less power. Just for fun, maybe we should try to do a third resistor that has 300 ohms of resistance. So a third light bulb with a 300 ohm internal resistance. So if we get a lower number than 72, then I guess the pattern holds. So P3 is going to be V squared over R3. So that's 120 volts squared divided by 300 ohms. Okay, let's see what we get. So 120 times 120 divided by 300, is it going to be less than 72? Oh, it is. It's 48. So 48 watts. So the pattern seems to be that a larger resistance leads to less power draw. So that's a interesting thing. For example, if you are, maybe you have like a child that you're doing like a toy robot with, and the toy robot, you put in a battery and the battery seems to die very quickly, and you're in charge of totally designing the circuit that powers the robot. The suggestion that I would make is maybe consider adding a little bit more resistance to the load so it will draw power a little more slowly. That assumes, of course, that you have ample an ample power supply, that the battery is basically high enough voltage to supply the current needs of your robot or whatever, even with a larger resistance added or with a smaller resistance added. In any case, it means that the one with the smaller resistance draws the most power and the one with the largest resistance draws the least power. Now we are moving on to the part of the chapter in which we talk about circuits in which we combine resistors in series or in parallel. So the question is, what's the total resistance of a pair of resistors which are placed in series if one has 10 ohms and the other has 40 ohms? So you might want to review the rules here for a series circuit. It says that the resistance total for a bunch of resistors combined in series is the sum of the individual resistances. So in this case we have Rs is equal to R1 plus R2, so that's 10 ohms plus 40 ohms, and I know some of you need a calculator to solve that. 10 plus 40 should give you 50. So the total resistance is 50 ohms in this case. Alright, so now let's look at another example, slightly harder example. This time you've got 3 resistors, 10 ohms, 20 ohms, 40 ohms, and you're going to place these in series, and then you're going to connect the whole series to a 140 volt power supply. So the question is, how much current is this circuit going to draw, and how much voltage drop is going to go for each resistor, and how much power does this circuit need? So that's a fairly complex set of questions to go with this. The approach is that you figure out what the total resistance of this circuit is, basically of this series combination of resistors. From that you use Ohm's law, and that gets you the current. Then once you have the current's the same for each of the 3 resistors, so you use Ohm's law again, but this time individually for each one, and that gets you the voltage drop across each. And then if you want to know how much total power the circuit needs, then you can use, for example, the ohmic power P equals I times V equation. So again, if you want to try to figure out what the resistance of a bunch of resistors in series is, you use this equation, Rs equals R1 plus R2 plus R3, etc. You get the same current through each resistor that's in series. You get a total voltage drop that's equal to the voltage drop across the first plus the voltage across the second plus the voltage across the third, and those voltages basically you can find using Ohm's law. So the resistance for this set of circuits of resistors should be R1 plus R2 plus R3, so that's 10 ohms plus 20 ohms plus 40 ohms, and so that is a total of 70 ohms. So that's the total resistance. Now you can use Ohm's law, V equals IR, and in this case the R is R series. That means that I is going to be equal to V over R series. So that is 140 volts, which was given, divided by that 70 ohms that we just found, and that gives you 2.0 amps. Okay, now the total power, therefore P is I times V, so that's 2.0 amps times 140 volts. So that is 280 watts. If you don't know how I'm calculating these, you can use your calculator to follow along. So now we got to find the individual voltage drops. So V sub I, or V1 is the voltage drop across the first, is going to be I times the resistance of the first, and so that's going to be 2.0 amps times 10 ohms. So 10 times 2, you might need your calculator to figure that one out, is going to be 20 volts. For the second one, we use I times R2, so that's 2.0 amps times a total of 20 ohms. Again, if you need your calculator, go for it. So 2 times 20 should give us 40 volts. For the third one, we use I times R3, and so that is 2.0 amps times 40 ohms. So if you need your calculator to get 2 times 40, go for it. But you should come up with 80 volts. So now we've solved for everything that problem has asked us for. So the answer to this question is basically the circuit uses a power of 280 watts, the current's 2 amps, the voltage drops are 20 volts, 40 volts, and 80 volts respectively for 10 ohm, 20 ohm, and 40 ohm. Notice that if you add up 20 plus 40 plus 80, what you get is, I'll let you use your calculator to double check this, but you get 140 volts, which is how much you started with. So that's a good double check to make sure that we've done everything right, or at least that we've done this part of it right. So what's the total resistance of a pair of resistors at 10 ohms and 40 ohms which are placed in parallel rather than in series? When you place resistors in parallel, what you end up doing is you get the same amount of current through each branch of your circuit. So each branch is each parallel direction that the current can go. And you get the same voltage drop across each, and you get a total current that's equal to the current through the first branch plus the current through the second plus the current through the third. The currents are not all equal in this case, unless all the resistances are. To find the resistance for a set of parallel resistors, you use 1 over the resistance total is equal to 1 over the first resistance plus 1 over the second plus 1 over the third plus etc. If you just have 2 in parallel, you can quickly solve this by doing a little bit of algebra, and that's actually one of your homework questions, so I'm not going to do that for you right now. But basically, the parallel circuit for 2 in parallel looks like the product of the two resistances divided by the sum of the two resistances. So the resistance for this set is going to be R1 times R2 over R1 plus R2. And so we were given 10 ohms, and that's going to be times 40 ohms. That's going to be divided by 10 ohms plus 40 ohms. You might want your calculators. I'll kill a little time for you to put some numbers in, but 10 times 40 is 400 ohms squared. 10 plus 40 means that we have 50 ohms on the bottom. So you can do a little bit of cancellation here with the units, and what you get is 8 ohms. And the rule is that if you have two or more resistors that are in parallel to each other, then the equivalent resistance of that must be less than the individual resistances of each of those resistors. So the lowest resistance was 10. We need to come up with a number less than 10. We got it. So the fact that we came up with 8, which is less than 10, is a nice double check to make sure we've done that part right. Okay, next example. Suppose that you have 3 resistors. One is 10, one is 20, and one is 40, and you place all 3 of them in parallel, and then you connect everything up to a 140 volt power supply. So what's going to be the current and voltage drop and so on? The power drawn by this circuit. Alright, so again, we need to first of all figure out what the equivalent resistance is. So we use the parallel resistance formula. So 1 over R1 plus 1 over R2 plus 1 over R3. So that's 1 over 10 ohms plus 1 over 20 ohms plus 1 over 40 ohms. Alright, so if you want to use your calculator, you might do it like this. There's 1 over 10, and then we need to have 1 over 20, and then we need to have 1 over 40. And so you come up with 0.175 inverse ohms. So all of this is basically 0.175 inverse ohms. And so the parallel total parallel resistance is going to be whatever that is, 1 divided by whatever that is. So we could do 1 over x and we come up with 5.71. So we'll call it 5.7143 ohms just for fun. Obviously, we don't have quite that many significant figures. It's really just going to be these 2 digits. Another double check to use here before I move on to figuring out power and voltage drops is that the basic rule is if you have 2 that are in parallel, then the total parallel resistance should be less than either individual resistor's resistance. Well, when you have 3, you can treat it as if you have 2 in parallel, which are then in parallel with 1 more. And so when we did 10 and 40 in parallel, we came up with 8. So that's like having an 8 in parallel with a 20. So we need to come up with a resistance that's less than 8, and we did. So that's good news. Okay, the next question was how much current is going through this circuit as a whole. So the current for the circuit as a whole looks like this. You use Ohm's law, V equals IR. So we can solve that. I is going to be V over R. So that's going to be 140 volts divided by 5.7143 ohms. And so the total current should be, let's pull out the calculator. Let's just do 1 over x for that, and then that times 140 gives us 24.5. So we'll just write 24.5 amps here. Again, there's actually only 2 significant figures to work with, so it's really going to be 25 amps. So what's the voltage drop across each individual branch of this resistor? Well, the voltage drop has to be the same for every single branch. So basically what that means is that every individual resistor is also going to have a voltage drop of 140. So V1 equals V2 equals V3 is equal to 140 volts. You could then figure out how much current is drawn by each individual branch. So for example, I1 is going to be V over R1, so that's going to be 140 volts divided by 10 ohms. And so that means that 14 amps are going to the 10 ohm resistor. I2 should be V over R2, and so that's 140 volts divided by 20 ohms. Okay, so that's going to be 7 amps. And then I3 is going to be the voltage over R3, and so that's 140 volts divided by 40 amps. So that is 3.5 amps. This one you could even put 7.0 if you wanted. Okay, last but not least, P is equal to IV, which is going to basically be 24.5 amps times 140 volts. So the total power draw is going to be this times 140, should be 3400. Okay, so 3430 watts, and of course this is 2 significant figures again, so there is our power draw. So 3400 watts of power. Voltage drop across each is 140 volts, which translates to 14 amps, 7.0 amps, and 3.5 amps respectively, and a total of 25 amps being drawn. These are using significant figures, so this plus this adds up to the 24.5, which is what we need it to do, and of course you have to round that to 25 for 2 significant figures. All right, let's talk a little bit about transformers. So we have a primary voltage from a certain power plant at 12,000 volts and a secondary at 120,000 volts. And we know that the primary has 200 windings. We want to know how many windings are in the secondary coil. So to solve for this thing, we use this voltage change for a transformer equation. That's the one that says that the output voltage is the output windings over the input windings times the input voltage. Or if you want, the secondary voltage is the number of windings in the secondary coil over the number of windings in the primary coil times the primary voltage. So we're solving for N2 in this equation. So let's see here. N2 over N1 V1 is equal to V2. So let's go ahead and divide both sides by V1. So that gets rid of the V1s. Let's go ahead and multiply both sides of the equation by N1. So that gets rid of the N1s. So we have N2 is equal to V2 over V1 N1. So that's 120,000 volts divided by 12,000 volts times 200 windings. So you may need your calculator to solve this one. Let's see here, there's all these zeros, and then we have 120 over 12. So that should be 10. That times 200 should give us 2,000. So N2 should have 2,000 windings. So that is how many windings we expect to see in that secondary coil. Alright, so that's our first transformers question. Let's look at another one. In this other one, we have that the secondary voltage is going to be produced by a transformer with 30 windings in the primary and 240 in the secondary, and the primary is 180,000 volts. We want to know, what is this secondary voltage going to be? So we use that same equation again, and actually we don't even have to do anything to it. We just plug numbers in. So we have 240 divided by 30, the windings part cancels, times 180, times 18,000 volts. So 240 over 30 is 8. So 240 divided by 30, and that is going to be times 18,000, and what you get is 144,000. So V2 is 144,000 volts. So that is what our output voltage from this transformer is. So the output voltage, of course, is also the secondary voltage. Now let's go ahead and look at a different kind of question with these transformers. Suppose you've got a generating plant and it gives you 240,000 volts and it's got a current of 10 amps. And the step-down process is going to increase the voltage up to 240,000 volts. What's the current going to be after this step-up process? This should say step-up. All right. So we use basically conservation of energy. It says that the power in should be equal to the power out. So this means that basically V1 I1 should be equal to V2 I2. So this is the input, this is the output. So what we've been given is that the electrical power that's been generated, the input in other words, was 24,000 volts, and that at output we should have 240,000 volts. We're also told that the input current was 10 amps. Okay, so we're looking for this output current right here. So solve the equation for the output current. I2 should be V1 over V2 I1, and so that is 24,000 divided by 240,000 volts times 10 amps. So quick mental math, this is a tenth of this, so that means that I2 should be equal to 1.0 amp. If you need to use your calculator to verify that, then be my guest. In any case, your output current should be 1.0 amps after the voltage step up. So you're stepping up the voltage, you're stepping down the current. Right. Suppose that the power lines have a total resistance of 10 kilo ohms. The plant is again generating 24,000 volts and again stepping up to 240,000 volts. The question here is, what is going to be the power in the lines both with and without the stepping up process? Well, to do that, we use P equals IV. So without the stepping up, what we have is this, by the way, using that V is equal to IR means that P is equal to V squared over R. So we would have 24,000 volts divided by this initial resistance, 10,000 ohms. And so you'd end up with 2.4 watts. Then at output, you should also, you've stepped up the voltage to 240,000, but you stepped down the current to basically 1/10 what it was before, and since P is equal to IV, that would be a factor of 10 decrease, so you're left with 2.4 watts again. So that means that your power at both should be 2.4 watts. Now with that said, the point of stepping up is that you basically lose less energy in transmission through these lines, and then you step back down to whatever voltage you're going to use at your source destination so that it's at, say, 120 volts or what have you. Well, that's all that I've got for today. So thanks for watching, and I hope that you find this